So let's talk today about a couple of things. And I think the homework itself was probably easiest, but let's just kind of formalize this of significant figures. Now actually, if you turn in your packet, actually no, let's back up a step, sorry. Let's just turn in your packet to page 1. We're going to just kind of walk ourselves through this, and we didn't start the podcast that we have on the server are different than that. So let's just kind of walk ourselves. So let's just talk about matter real fast. So what do you know about matter? It takes up space. Good. So it takes up space. And two things. It has mass. So it has mass and it takes up space. That's the definition of matter. Very simple, okay? And so, but matter, if you look at that cool chart that we have on that table there, there's two kinds of matter, right? And you already got the chart there, but you can see there. There's homogeneous mixtures and there's heterogeneous mixtures. All right. And chemistry land, we talk about primarily homogeneous mixtures because that can be broken into what we call pure substances. When you talk about pure substances, there's two varieties of pure substances. There are compounds and there are elements. What's a compound? Actually, what's an element? Let's do an element first. So on your paper, you're going to make some notes here about elements here. What's an element? Rusty, what's an element? It's one of those things. All right, you find them on the periodic table, don't you? There's roughly 100 of them, 100 and some change, right? Right? So we have, if you look at the periodic table, there's 114 or whatever elements on the periodic table. But what's actually kind of like the definition of an element? Go ahead. Yes, simplest form of matter. That's a little bit, why is that a little bit weird? Because we know that elements consist of, well, elements and atoms are really the same thing. But if you break an atom down, you find protons, neutrons, and electrons. And guess what? You can break down protons and neutrons into quarks and leptons and all kinds of weird things. So it's some level. It is definitely the simplest form of matter. But it's kind of the basic piece of matter. All right. Now, if we look at a compound, what's up with a compound? How's that different than an element? Yeah, Mr. Lay.
Isn't it something made up of just like a carbonate that's a compound because it contains carbon and oxygen?
Actually, that's a polyatomic ion, and then it's found in an ion, or it's found in a compound. Good thought. Think of like a molecule. Can somebody think of a molecule? A particular molecule? A molecule that would contain, molecules have nonmetals bonded to nonmetals. So a simple carbon dioxide. So carbon dioxide is a compound that contains carbon and oxygen. In fact, the Lewis structure, if you recall from last year, looks like that. That is one contiguous compound. And so in a molecular structure, it actually looks like that. Linear triatomic, and that is a compound. There's a chemical bond between the carbon and the oxygen, and that makes it a compound. Other examples of compounds? Huh? Water, yeah, H2O. Water looks like a Mickey Mouse head, right? The O, and then the two H's are the ears. Okay? Any other compounds? Think of an ionic compound for me. Sodium chloride, yeah, NaCl. That's a compound. And actually, interesting thing, if you recall with ionic compounds, is that instead of, if I go back here to the carbon dioxide or whatever, this is actually the carbon dioxide right here. It's one small piece which got one carbon and two oxygens. How is that different than, say, sodium chloride? Is it one Na connected to one Cl? It's a ratio, that's right. So the Na is connected to the Cl, connected to the Na, connected to the Cl, connected to the Cl, connected to the Na. Actually, we call it a lattice structure. And they go on and on and on. There's sort of this never-ending pattern, and it's three-dimensional. So if you look at a crystal of salt, right, you get the idea here. I'm trying to draw it in 3 dimensions, possibly poorly, but you get the idea. So you have this three-dimensional array. So if you have a small piece of salt, and you're looking at a small piece of salt, you'll see it's actually a cube. If you look at have you ever looked at a piece of salt? It looks like a cube, and it is NaCl, NaCl, NaCl. And actually, if you kind of do the math here, each Na is surrounded by how many Cls do you think? Can you think about it spatially here? 4 is not correct. Three-dimensionally. 6 is correct, and each chlorine is surrounded by 6 sodiums. All right, if you kind of look at that, right? Because you've got 1, 2, 3, 4, and then there's the one kind of coming out of the board at you, and then the one going up, if you kind of look at that Na. You see that? So but the pattern, we say NaCl, but it's like Na 10 billion, Cl 10 billion, but the ratio is 1 to 1. If you have calcium chloride, for example, CaCl2, it's also a pattern, although it's not going to be a nice pretty cube. It's actually quite a bit more complex in its structural formula, but it's still just a 1 to 2 ratio. So Ca a billion, Cl 2 billion is the ratio, ionic. And how can you distinguish an ionic from a covalent? Yes, Beth Ann, that's correct. This, of course, is a metal bonded to a nonmetal, right? And then back here with our molecular compound, or our covalent compound, that's a nonmetal bonded to a nonmetal. Now, just good review. How do you know if something's a metal versus a nonmetal? Charge, sort of. Where it is on the periodic table, right? On the periodic table, there's the stair-step line, right? Where are your metals? These are the metals, and these are the nonmetals. There's one exception, hydrogen. Hydrogen is a nonmetal, even though he's over there. Everybody else got it? So that's how you can know. So if I have an ionic compound versus a molecular or a covalent compound, same ballgame. Okay? Just kind of bringing back some memories here. You're going, oh yeah, But it's been, what, 3 months or 2.5 months since you probably taught chemistry stuff. So we've got compounds, and of course compound elements are made of atoms. You can see that on the table. And of course the atom has a nucleus and it has electrons. And while we're at this, let's just talk about the atom. You should be writing these kind of in the sort of white space around there. If you take an atom, atoms are really, really what? Small. And if you recall the analogy, we'll use this analogy. I think we had this last year, but we're going to go ahead and say it. If I have the world, okay, I have to do attendance. Okay, thank you. If I have the world, no, I do this right. This is not a world. This is an orange. Jumping ahead. How many atoms in an orange? A lot. To do that, you would have to blow up the orange to the size of the world, and the atoms would be the size of cherries. So imagine the world filled with cherries. Okay, tiny cherries. Well, not tiny, but cherries. And then you stuff that many cherries into the world. That's the same number of atoms that are stuffed into an orange. That's a lot. It's a huge number, isn't it? Okay, and then the crazy thing about this, of course, is that if I were to look inside of that cherry, and I blew the cherry, which is in the world, up to the size of the Earth, not the Earth, I blew it up to the size of this room, the nucleus would sit in the center, wouldn't it? And it would be the size of, so if we think of a ball the size of this room, that was the diameter of this room, how big would the nucleus be? The answer is it would be invisible. It would be too small to see in this room. For us to truly see this, we'd have to blow it up to the size of the ball the size of a football field. So if I talk about the nucleus now this is the cherry in the Earth, which is really, 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 really small. if this is now a ball the size of a football stadium, so you can go outside and make a ball the size of our football stadium. Actually, it needs to be a bigger football stadium than that, but double, you know, like a regular football stadium, as in like a NFL, like a Mile High Stadium or something like that. Then the nucleus is now the size of a marble, or maybe a cherry or whatever. And what's in between here and out here? Well, actually, what is out here? Electrons. And the electrons are like pieces of dust. So what's in an atom, mainly? Empty space. Nothing. It's empty. It's weird. When Ernest Rutherford figured this out in 1914 or whatever it was, he said, it was as if I shot a cannonball at a piece of tissue paper and the cannonball came back and hit me in the face. This doesn't make any sense. But it is the way it is. So we have a whole unit on the atom, or Chapter 7. That's kind of towards the end of the year. Even though it's Chapter 7, we jump around a little bit. But it's crazy. Crazy small. So, atoms. Good? All right. Say again? That doesn't look like a football stadium? Oh, I missed that. Yeah. Yeah, I was one thing out of the money last year in fantasy football. I lost because of a snowstorm. And my team, I had this great passer, the guy from Cleveland, and they had a snowstorm and they handed the ball off the whole game. They never handed a whole game. So I lost. It was bad. Oh well. Anyways, lost my train of thought here. Oh, next page. Let's go to page 2. Mixtures. There's homogeneous and heterogeneous. Let's just quickly talk ourselves through this. What's the definition of a homogeneous mixture? Homogeneous, of course, means the same. So does this, it is a consistent mixture. So you have a consistency, if you will. What's an example of a homogeneous mixture? So in a homogeneous mixture, every sip, if it was a aqueous solution, would be the same. Okay. A soda would be a good example, yeah. Other homogeneous mixtures? Water is a compound, so no, that would not be true. Good thought. So it has to be a mixture. And a mixture is where you take two or more compounds and or elements and mix them together. So a soda is a mixture of water, and then dissolved in the water is sugar, carbon dioxide, flavors, etc. And then hopefully every sip of your Mountain Dew or your Pepsi or whatever is going to be the same. It has like little floaties and stuff in it. Then it's not homogeneous. Any other homogeneous mixtures? Milk, yeah, huh? Other examples? Think of non-liquid ones. Everybody take a deep breath. Air is correct. Because air consists of 80% nitrogen and 20% oxygen. Actually, the 80% nitrogen is actually probably 79%. And then there's actually 1% of other gases, carbon dioxide, argon, etc. And in varyingly small percentages. So usually we just think of it as 80-20. It's really 79-20, and then you got this extra bit. So that's some good examples of homogeneous. What about heterogeneous mixtures? So they're not consistent, right? I like to think of them as the lumpy ones. An example of a heterogeneous mixture. Huh? I can't hear you. Rocks, yeah. So if you go grab a rock from Pikes Peak, or just from your backyard, which probably came from Pikes Peak, it's got like a bunch of little crystals. Is every rock kind of the same exact number of crystals? Of course they aren't. So it's not consistent, is it? All right. One of the big problems in chemistry land or the world is that it is pretty heterogeneous in its just kind of out in nature. And one sort of the big projects of scientists is that scientists want to make things more homogeneous. So they want to separate out the stuff. If you go up to Cripple Creek, right, and you go to the mine, what do they want to get out of the Cripple Creek mine? Gold. So their goal is to find the gold there. Well, there's this huge mountain. I think top drawer, I mean, like, how many pairs? Lots of pairs, or? Yeah, I don't know. That's a heterogeneous, it's just a big mountain they're digging up, right? Anybody been up there? You know what I'm talking about? They just got this big pile of dirt, basically, and rocks and junk, and they have to extract out of there the gold, right? And so how do they do that? Well, they have to come up with a process to get rid of the stuff that doesn't matter, the dirt and the junk that's like, well, we don't need this. How do I get it into a pure form of gold so I can sell it for $800 an ounce or whatever the price is these days? It's very high these days. So that's a problem. And so one big job of chemists is to figure out what's a process to separate that mixture out so that I can get the good stuff out, the gold in that particular instance. How do I get it out so I can make it economical? And is it worth it? I mean, because, actually there's more gold in the oceans than is imaginable. But the problem is, of course, extracting it from it costs more than the gold's worth. We know how to get it. I can go grab 5 gallons of seawater, and you can take that and you can extract the gold out of there. Problem is, it costs a lot more money than it's worth, because you don't only get just, I don't know what the 5 gallons would produce, but just a teensy-weensy bit of gold. But there's gold in that water, but it's not economical to get it out. So, because the world is it's all mixed up. Actually, there you kind of have a homogeneous mixture, but it's in a very small, but it's in such a small concentration. To get it out is just too expensive. All right, separation. How do we separate mixtures, as I kind of said there? So still here. How do you separate a mixture? You have to use what we call a physical means. So this is the gold guy has to figure out a way, the gold chemists, basically the chemists who were working there and have figured this process out up in Cripple Creek at the mine, they figured out how to extract this stuff from the dirt. It's not like in the old days where they could just see it and grab it. It's all kind of just mixed in the dirt. And then they have a process, and it's a chemical, physical process from which they separate it out. Of course, they want to take rocks that have a higher concentration of gold, so they dig around for it. But sometimes they just take all this dirt, put it in the vat, go through this process. Once it's done through the process, you get gold. So they can add chemicals. So physically, what do we mean by physical properties? Okay, what is a physical property? Think of a physical change. Yeah, you have texture, yeah. But when you think of physical, when you change something physical, you don't change what it is. You just utilize its physical properties. So, for example, what would be a good physical property? Huh? Now, rusting is a chemical thing. Color, yeah, color, okay, good. But actually think of things that are typically more measurable. Not weight, but there's something like weight. No, not mass. Density, good. Actually, this is one of the huge ways that miners, or people who work in mines, will separate mixtures. Some things are more dense than others. And so they will actually have these slurries. They'll add water to the dirt. Some things float. Sometimes you want the things that float, and sometimes you want the things that sink. Depends on what you're after. If you want the stuff that floats, they just skim it off the top, and then they do more processes on that, and then they throw the stuff that sinks to the bottom. Sometimes you want the stuff that sinks, the stuff that floats and or dissolves. They wash away. They're done with it. Sometimes they want the things that dissolve. So another important one is solubility. Like that's actually the gold thing. It's gold something. It's actually not. It's not just chunks of gold. It's actually a compound of gold, and they can use solubility. And then they add a chemical, cyanide, some kind of a cyanide. It's sodium cyanide. And they extract it, and then they do another process. It's quite a big process to get that gold out. That'd be fun to go up there and kind of see them do that process. Other things like boiling point. Okay. So if I have a mixture of two different liquids, and one has a high boiling point, and one has a low boiling point, if I heat it up, what's going to happen? What's going to boil first? The low boiling point chemical, right? And then so if you can collect the gas, which is the low boiling point chemical, you can purify it. You get the low boiling point chemical first. Okay? In fact, that leads us to this next bullet point, or distillation. Distillation is pretty cool. You've got a picture right there. That's using this concept of the boiling point, this picture right here, right? And it kind of looks like this. And then another flask like down like that. I didn't draw that very well. But if I have two liquids, let's say one boils at 100 degrees, water, and then one boils at, say, 58 degrees, what happens is that the 58 degree stuff goes over here, and of course it's going to cool, and it'll recondense, and you will have a pure form of the lower boiling point chemical. In fact, the example I'm using right here, I don't know if you realize this, 58 degrees is the boiling point of C2H5OH. Anybody know what that is? This is alcohol. Ethanol, the chemical that, you know, is in beer and wine. Okay. Problem is that how do they make hard liquor? Remember the old days of the moonshiners? You ever read about that in your American history class or whatever? What's up with that? They had this thing in the 1920s, I believe it was, called Prohibition, right? What happened in Prohibition? They banned what? All alcohol. You couldn't sell alcohol in America, right? Couldn't do it. So in the back 40, what did Uncle Ernie do or whatever? He had what'd they call that thing in the back? They called it a still, didn't they? He had a still back in his property, right? A still comes from the word distill. So what they would do is they would take the alcohol and they would boil it. Thank you very much.
You are more than welcome.
They would take the alcohol, they would boil it, or actually, let's back up. How do they make an alcoholic beverage, wine or beer? You know? They ferment it. Good. So they have sugar water. Okay? They have sugar water, and it's going to have other things in there, but just for the sake of argument, like take a wine. They have grapes, right? Grapes have sugar in them, right? You ever had a grape? Tastes sweet, doesn't it? So what else goes into the wine when they're making the wine? A little biological thing. Yeast. These little critters called yeast. You stick yeast in sugar water or grape juice, and you let it sit for a time. The yeast are little animals. There's some kind of little critter. You biology people knows better. And they eat the sugar. And what is their waste product? Alcohol. So their waste product is alcohol. That's right. And so what happens is, of course, as time goes on, their waste product, which is the alcohol, builds up to a higher percentage. 1%, 2%. But then here's the bugger. When it gets to 5% or 6%, I don't know the exact number, they die. Because, well, they're kind of sitting in their own wastes and it kills them. You can't survive. They can't survive that high of a content of alcohol. It kills them. So the highest you can ever make some kind of an alcoholic beverage is like 5 or 6% alcohol. Are there alcoholic beverages that are higher in percentage than 5 or 6%? Surely there are, right? That's where you get the hard liquor. How do they get the hard liquor? Well, that's how they get it, with a distiller. They heat it up. They heat up the stuff, right? And what comes off is the pure alcohol. And the water stays behind. And if they heat it up long enough, they'll bring a little bit of the water with it. And then they'll add other flavors, to get the, I don't know, the different. I don't drink alcohol, so it's vodkas and the Everclears and all those kinds of things that people drink and whatever. Okay? So it's a mixture. It's just basically using the concept of boiling point. One has a lower boiling point than next. Another classic example that's very important in our world today is it's called fractional distillation. You have these columns that are probably 10 stories tall, and at the bottom they put what's called crude oil. Okay? We get this from the Middle East. Big debate in this presidential candidate deal going, right? What are we going to do about energy? That's all I can see if I turn on the TV, watch the Olympics. And what is crude oil? They sell it by the barrel. It's $120 a barrel today, or whatever the heck it is, right? Crude oil. Crude oil is a mixture of many, many different chemicals. And some of them has very low boiling points, And so actually what they do is they have pipes that come off of it at different heights. And again, this is like could be as high as 10 stories tall. The ones that have the lowest boiling point come out to the all the way to the top, and then the ones at the bottom, they never boil. They have high boiling points. This is the low boiling points are things like propane that you use in some of you may use to heat your house, but I use it on my grill, right? That kind of a thing. Right here you have octane. Octane is for gasoline. That's the stuff that's in your car. And down here, the stuff that doesn't boil and they kind of scrape off the bottom, that's the tar they put on the roads. And that tar, of course, you don't want it to just evaporate, right? You want it to kind of stay solid. But you've seen them put tar on the roads. They did a bunch of projects here this summer, right, doing road work and whatnot. And they take it, they heat it up, right, and it stinks a lot, right? And then they put it on the road, and then it solidifies. So they heat it up to its melting point, and it's that tar. So out of a barrel of crude oil, they get lots of different products. They get low boiling point things, and they get high boiling point things, and everything in between. And this is the octane. This is your gasoline. And they just have these columns, and they these pipes, and this goes, to another pipe that then, goes to a truck, and the truck sends it to your local gas station. But some of the stuff goes to other things. One of the other interesting things, they usually get too many low boiling point things, and so then they have another process. It's a chemical process where they call it cracking. What they do is they take the products and then they join them together, and they take the low boiling point ones and they make some more octane, because there's a bigger market for octane than there is for propane, because we drive cars a lot more than we use propane gas. So, okay. Chromatography. I think last year, if you recall, we did chromatography. One of our first take-home experiments. What you would do is you take if you have a solution here. What's a solution, by the way? Let's chat about that. What does that mean? What's a solution? In a solution, you have two parts of a solution: solute and solvent. So the solute is what you're dissolved in. So a can of pop. The solvent is what? Water. Good. And the solute is lots of solutes, actually. Sugar, carbon dioxide, etc. The solute's what get dissolved into. The solvent is what you dissolve. I didn't say that right. The solvent is what you dissolve into. The solute is what's dissolved. Okay. But if I have a particular solution and I want to have, and it also could be two liquids, like, alcohol and water, all right? Okay, I don't know why I'm on that train. If you then take a piece of paper, and they have special paper, some of it will travel up the paper more than the other. And if you look at the picture on the bottom of page 2, it's not very, it's black and white, but those actually have colors, and you can actually separate them based upon how far they travel in the paper. It actually has to do with how attracted it is to the paper or not. If it's really attracted to the paper, it only travels a small distance, and if it's attracted not very much, it will travel farther. And then they can actually measure the distances of their travel, and they can identify what chemicals are in there. Kind of one of those CSI kind of things. If I have a chemical, they have paper, they have that kind of chromatography. They actually have gas chromatographs where they can identify a particular chemical based upon what's in there. So if I have a mystery chemical found at the crime scene, I can figure out what it is. Okay? So that's just kind of some jogging your brains on what you learned last year. Like, oh yeah, solvents, I get this stuff. All right, sig figs. I think we talked about this. It looks like you got that, but let's just do a real quick review of sig figs. Actually, let me say one thing about sig figs. Where we say why sig figs. First of all, on the AP chemistry test, and it's hard to think about that right now because it's a long ways away, right? But on the AP chemistry test, I like to think that the big rule is that you want to have 3 sig figs. Why is that? Actually, the rule is if you make a mistake on a mathematical problem on the AP chemistry test, if you are off a significant figure error, and if you are off by 1 significant figure, that's okay. So let's say that the correct answer is 2.07 grams, but you write 2.072 grams. You're technically incorrect. You are off by 1 sig fig. You've put 4 sig figs when, say, the correct answer is 3. Or you write 2.1 grams, which is this rounded to 2 significant figures, right? You are off in both cases by 1 sig fig. They don't care. If you're off by 1 sig fig, you're fine. If you're off by 2 sig figs, so if you write 2.0720, they will take off a point. Okay, so this has 5 sig figs when the correct answer is 3 here, okay? But here's something I've always seen. I've never seen them have more than 4 significant figures on a problem. I've never seen them have less than 2. It's either 2, 3, or 4. So my rule is what? Go with 3, because you can never be wrong. So your answers always put 3. I mean, if you see there's 4, go ahead and put 4. I mean, but just, you can never get it wrong if you have 3 significant figures. Now, just to recall, there's this whole thing with the zeros. This number has leading zeros, and leading zeros don't count, so this has 2 sig figs, right? If I have a trailing zeros are weird. If I have 2,000, that has 1 significant digit. But if I have trailing zeros with a decimal, those all count. All right? And there is one that's kind of weird, okay? If I am talking about pH and or POH, okay? If I say 3.72, how many significant digits if this is a pH? This has 2 sig figs. You see, Mr. Bergman, that makes no sense. All right, with pH, it's sort of a special rule for pH and POH. You only count the numbers past the decimal. You do not count the number in front. The number in front actually is the power of 10. If you recall, pH is the negative log of the concentration of the hydrogen. So the real number that's actually measuring is the number that came in the calculator. So if I've got, 5.32 times 10 to the minus 4th, and if I take the negative log of that, let me get my calculator out. So if I take the log, or negative log, of 5.32, remember use the double E button, and negative 4, I get a pH of 3.27408. So I take the negative log of this, I get 3.27409. That's what my calculator says. How many sig figs can I keep? 3 here. So the real answer is 3.274. Because this 3, if you really look at it, is related to this 4 right here, the power of 10. It's off by 1 because of the fact that it's 3 or whatever, but that's why this is giving you the power of 10 is what it is. Now, the very odd thing, I'll see this one, 12.72 has how many sig figs in it? If it's a pH or a POH? Just 2. This is where people, particularly when you have high pHs, this is where people tend to truncate it. They'll say, well, I'm supposed to have 3 significant figures, and so they write 12.7. And now they're going to be wrong, because now they've only written 1 significant figure. You see? They think they have 3, but they've only got 1, because the 12 relates to the power of 10, and the 7 is the rest of it. So watch that when you do pHs and POHs. That's where it's a common mistake that you don't want to make. Okay? And then, of course, the rules on multiplication and addition and subtraction and all that stuff. What do you do with that? So if I think that's the next page. Why do I have way too much space? Multiplication and division. If you get your calculators, would you go ahead and get those out? So what do we got here? We're going to do a little density problem. I've got a very small volume, and I've got this many grams. What would be the density of this substance? So what does your calculator say this answer is? Somebody with a calculator here. 8.32 divided by 0.015. What do you get? It'd be a big number, I think. Huh? 5.5. That's pretty good. How many sig figs in 8.32 here? 3, and how about in 0.015? How many digits can I keep? So what do? You're going to truncate it here, so you write 55, right? No, it's 550. You have to make that 4 a 0. Don't say 55. You still have to have 550 something, right? But you have to lose the 4, right? You're only as good as your worst measurement. So what's your worst measurement? The 2 digits down here on the bottom. And so that's where you need to kind of pay attention, right? You're only as good as your worst measurement. And you do multiplication and division. So what if I have 0.0018 times 0.008350? I don't know what this is, but we'll do this. So what does your calculator say the answer is? Somebody. 1.503 to negative what? 5. All right, let's count our sig figs. In our first term, I have how many sig figs? 2. In my second term, I have 4. This 0 counts. He's a trailing 0, but there is a decimal. So I can only keep 2. So the answer is 1.5 times 10 to the minus 5. One thing nice about scientific notation is you just count the digits. It's always going to be, you just count the first 1, 2 digits, you know, and then you just truncate. If this 0 is a 6 or something like this, if this had been a 6 right here when we did the math, that would make this what? 1.6 times 10 to the minus 5. It isn't, so, but just kind of keep that in mind. What about this whole addition subtraction? What if I take 102 plus 8.36? So it's 102 plus, I'm going to line it up, 8.36. Well, that's 110.36. That's what my calculator says. The real answer is, you can only be as good as your worst measurement. My worst measurement is actually from the 102, and it's only accurate to the ones place, so I need to round to the ones place. So actually, this is a little tricky. What's the answer? Is that correct? No. I have to put a decimal here because I need to indicate that that 0 is actually a measured number. So I can't say, you know, if it was 112, if it added up to 112, I can just write 112. But because that's a 0, I do have to indicate that that 0 is significant, so I have to put a decimal there. Or, of course, the weird one, right? I think this is like, what's 100 plus 67? You'd say it's 167, right? And you'd be wrong. No. What is 100 plus 67? It's 200. What? Remember, 100 is only one significant digit. 67 has 2 significant digits, but this is accurate to the hundreds place. You get 167, but you need to round to the hundreds place. How do you round to the hundreds place, 167? You have to round the 6 up there, and you get 200. That is a weird one, isn't it? Now, this would be very unlikely, because what you're essentially saying is you have a crappy measurement in the number 100, and you have a relatively decent measurement in 67. Maybe it would be like this. From here to Denver, it's 100 miles. Let's say I take a particular point in Denver. I'm going to take the Pepsi Center. From right where we're standing to the Pepsi Center is 100 miles. Okay? Is that accurate? It's probably close-ish. But it's a crappy measurement. But let's say then from the Pepsi Center to Fort Collins, I have a friend who took his GPS out and drove from the Pepsi Center to his house in Fort Collins. I think that's about 67 miles. And he measured, and it was 67 miles. So he has a good measurement. And then we have this Bergman estimate. How far is it from here to Fort Collins? About 200 miles. That's all I can say, because the first measurement isn't done very well. The second one is really good. Usually we like to add measurements that are of similar levels of accuracy. So this is a sort of weird extreme case. Okay? All right. And we have one more topic to cover today. Let's talk about dimensional analysis. So next page. How do we solve dimensional analysis problems? Hold that thought while I think about this here. All right, so dimensional analysis. You understand dimensional analysis? This is where we do the railroad track thing, right? So I don't know if I'll do a one-dimensional problem for you. Well, let's do one. Okay, this September, I think I told you I'm going to do a triathlon. Actually, It's an aqua bike, so it's only 2 events, but what the heck. I'm going to ride my bike 112 miles in this race. How many kilometers am I going to travel? What do you do? You may not know the conversion. I have it in my head, so you're good. What do I do? So how do I do that? Miles on the bottom, kilometers on top. I know that 1 mile is equal to 1.6. I think it's 0.8. I may be wrong, but that's pretty close. 1.6 something kilometers. I think it's 1.608. The miles cancel. How many kilometers? So all the guys who are going to be doing this race from Europe, they would not even think of it as 112 miles. They would think of it as, someone with a calculator? 180. Is it right at 180? 0.096 kilometers. Of course, they would just call that 180 decimal kilometer, because this does have 3 significant digits, and I'm assuming I did this right, and it has 4 significant digits. So it's a 180 kilometer race for them. Good? Remember how to do that? Hopefully that's going to come hold hat. Okay, now what if I have a more multi-dimensional problem? So on top of page 5. So if I want to do 55, let's do something besides 55 miles per hour. Let's say that, well, I hope to travel. Let's see, we'll do this. I hope to travel on my bicycle in the race. I hope to travel about 21 miles per hour on average over the 112 miles. How many meters per second will I be traveling on average? It'll vary because, you know, when there's a hill, I'll go slow, and when there's downhill, I'll go fast. It's actually a pretty flat course, but so what do I need to do? Go miles to kilometers, and I'm going to assume, by the way, that I'm right. 1 mile is 1.60. You know, it's 1.609. I remembered now. It's coming into my brain, and that should be miles. The miles cancel. Now what do I do? Kilometers to meters. Now, do you know that in your head? It's 1,000 meters in a kilometer. Kilometers cancel. Now I can work with time. Now, tricky on this, hours is on the bottom, so to cancel off hours, you have to put it on the top. So hours to seconds. 1 hour. And you know how many seconds in an hour? I'm going to do a quick, there's 3,600. You can do hours to minutes and then minutes to seconds if you want, but you just do this. And then the hours cancel, don't they? And I'm left with, if you look here, meters per second. So remember, numbers on the top are multiplied, numbers on the bottom are divided. So it's going to be 21 times 1.609 times 1,000 divided by 3,600. How many meters per second? Every second, how many meters will I travel? 9.4, maybe? Because I only have 2 significant digits. So 9.4 meters every second. That's pretty fast if you think about it. 9 meters is 30 feet-ish. So 30 feet a second. That's when you're going 21 miles an hour. So I think it's possible. I did I did a training ride on last week. Wednesday, maybe? Whatever it was, Tuesday. Down near the Air Force Academy and up in Monument, a very hilly course. And I was averaging 18 miles an hour for 107 miles. So on a flat course, when I'm not so tired and whatever, I think, plus I had to stop at stoplights and, you know, things like that that always slow you down when you're on a training ride. Well, when you're in a race, you always go faster. So I think it's a reasonable time. All right. And then what about the sort of meter problem when you have a meter cubed, right? So if I've got, if I want to convert 3.7 cubic meters, and I want to convert it to cubic centimeters, what's the trick on that? You do it right at 3 times. So you can say 3.7 meter, meter, meter. You have to convert it 3 times. I'll show you a shortcut just in a minute, but let's do it the long way first. So you can go meter to centimeter 3 times. 1 meter is how many centimeter? 100, right? So you do this 3 times. So you can cancel the meter out 3 times. So 3.7 times 100 times 100 times 100 is a lot. I don't know, what does that come out to be? 3,700. Somebody with a calculator, what does that come out to be? top left drawer. So what do you get? Huh? 3,700,000. Now, if I was to do this, let me show you something. There is, if you understand that it's like meter, meter, meter. This is what the old way they teach, and probably your textbook does this. If they said 3.7 meters cubed, this is what you could do this. You could say meters cubed, centimeters cubed. You can say 1 cubed and 100 cubed. Less writing to do. You're still doing the same thing, right? But this is how you do this. I keep getting emails. There you go. So you get the idea? So that's a shorter method, and then the meter cubed cancels. So for our regular chem, we always just teach them the meter, meter, meter. And if you want to use that, just knock yourself out. But this will save you some paper and some writing if you think about it. Okay? And then let's do one more. A complex problem. Gold. Speaking of gold, gold has a density of 19.2 grams per cubic centimeter. I want us to convert to pounds per gallon. So if I had a cubic centimeter of gold, which is a very small amount of gold, a cubic centimeter is like 1 milliliter, a tiny little cube about that big of gold, it would weigh 19.3 grams. But what if I had a gallon jug filled with gold? How much would it weigh? An interesting question, isn't it? So we could figure the answer out. It's just a conversion, though. We've got to convert grams to pounds, and we've got to convert cubic centimeters to gallons. So I would say 19.2 grams over 1 centimeter cubed. What do you want to do first, the mass or the volume? Mass. That's kind of easy. So what do I do? Grams to pounds. Now, you may not know these numbers. I have them in my head. I know that's sick. Okay. There's 454 grams in 1 pound, so the grams cancel. Now we need to convert cubic centimeters to gallons. Now you may not know these conversions, but I can go from centimeters cubed to milliliters, milliliters to liters, and liters to gallons. So it's going to take a several multi-step problem to do this. So I can say, now I got centimeters cubed here, what am I going to go on top? Centimeters cubed. 1 centimeter cubed is equal to, anyone know this one? This is kind of an important one to know. 1 milliliter. It is the definition, in fact, of a milliliter. It is a cubic centimeter. And then I can go from milliliters to liters, and there's 1,000 milliliters in every liter. And the milliliters cancel. And then I can go from liters to gallons. So 1 gallon is equal to 3-point-something liters. I'm going to say 8. I don't remember that. I think it's 3.79 or... Huh? It's something like that. I don't know. It's something like this. I don't recall the exact number, so we'll get estimates. This is where we'd want to look it up on a table, and I don't have it. Okay? So, somebody with a calculator. I got a gallon of gold. How much does it weigh? £160. I weigh about 160 pounds. So 1 gallon, think of a gallon jug, that would weigh the same amount as me. Okay? So that gives you kind of a sense of how dense gold is, right? That's kind of cool. Good? Is that ringing some old bells for you?